convoy, you're cleared onto the east taxiway at Alpha.
Roger, Bravo.
Andrews Air Force Base, home of Air Force One, the president's heavily guarded plane.
Bravo leader, continue eastbound, Delta 3 to Echo.
Roger, exiting taxiway at Delta 3 to Echo.
But this armed convoy has another mission. It's headed for a remote hangar where a special cargo was delivered earlier.
Charlie 1 offloading crew. Are we cleared for entry? Roger, Charlie 1, you're all clear here.
Military guards set up a perimeter while a well-coordinated team of professionals goes about its business. Their objective? Secure the cargo for transport during the night.
Transport 1, you're clear to move into position. Roger, moving transport 1 into position.
They take no chances. This cargo is a top priority for the U.S. Army.
Roger, we'll be departing at Echo 3. Roger, Echo 3.
Beneath the canvas shroud is a new weapons system so advanced it is virtually undetectable by enemy forces.
Charlie 1, we're hailing the vehicles ahead.
In development for nearly 20 years, it is possibly the most sophisticated weapon the Army has ever fielded.
Over Key Bridge. Repeat, convoy cleared over Key Bridge. Charlie leader, the convoy will be returning right on Pennsylvania Avenue. Roger, Charlie leader. Bravo 1, we're signaling the truck ahead to clear the area.
Tonight, it is on its first official mission. Destination, the nation's capital.
Transport complete. Roger, Bravo leader, area is secure.
Comanche, the most advanced helicopter the world has ever seen.
Hello, I'm Nick Lapis. I'm a test pilot, one of only a select few who's ever flown the Comanche. And as a former Army soldier who flew helicopters in Vietnam, I can also tell you that the battlefield will never be the same should Comanche go to war. It performs like no other helicopter. In fact, it's a complete cybernetic weapons system. It's the world's first and only stealth helicopter. It can fly at treetop level by the light of the stars, penetrate deep into enemy territory, and return undetected, even by radar. But its real power is in its brain. Comanche has supercomputers and infrared sensors that can size up the battlefield, pinpoint targets, and speed that information back to the ground commander, all in a few seconds. Nothing has been able to provide that before. Not satellites, or spy planes, or all the other eyes and ears on the battlefield. Comanche will provide the information to win future wars. Our story isn't just about how Comanche flies. It's about how a team of military and scientific visionaries harnessed technologies that were little more than theory when the process began 20 years ago, and how Comanche evolved into something more than just another helicopter, into a true cybercopter.
January 17th, 1991. In response to Iraq's invasion of Kuwait, the U.S. and coalition forces launch Operation Desert Storm. Never before had the world witnessed such decisive use of military power. The world's first glimpse of the digital battlefield not only revealed the enormous power and devastation it can render, but the decisive role information dominance can play.
Desert Storm really provided a revolutionary look at what new weapon systems will do on the battlefield. We call it the digital battlefield, but that is really what might be called the computer battlefield or the information battlefield. Information for the future is absolutely key. He who has the best information will win the next battles.
When you solve those three questions, where am I, where is the enemy, where are my buddies, you revolutionize warfare. You really solve a lot of tactical problems that have confronted soldiers from the beginning of time. And that's what we're really about in information warfare.
On the nonlinear battlefield, we're talking about more risk, not knowing where the enemy is. Could be behind us, could be on our flanks. It's more free-flowing. Information is essential. In other words, those set boundaries are no longer clearly defined. The enemy blends into his environment. Maybe an urban environment, maybe a jungle environment. But what it clearly is more risk, less well-defined, and a much greater threat to our soldiers.
In the jungle environment of the Vietnam War, information was at a premium. The 1st Air Cavalry not only proved the usefulness of the helicopter in combat, but also its value in locating enemy forces.
In Vietnam, the Army helicopter really came of age. It was a helicopter war. And one of the chief things that the helicopter did was reconnaissance, which was really go out and look for the enemy. It was the best piece of equipment we had available for that mission.
I flew hundreds of reconnaissance missions in Vietnam, and there we relied on visually finding the targets and verbally reporting them back upstream, and it could take literally hours to get fire back on the target or troops back on the scene.
While the Army recognized the value of helicopter reconnaissance, it also learned its limitations. Helicopters were slow, noisy, and could not operate safely at night. And new enemy weapons presented even greater threats.
Toward the end of the war, we saw the advent of the IR missile, the infrared missile, that could seek the heat from a helicopter. That was devastating to our helicopters, and we knew right then we needed a system to defeat those infrared missiles. Following that was radio frequency guided missiles, or missiles guided by a radar, and we had to defeat that too.
One of the bitter lessons we learned in Vietnam was how vulnerable helicopters can be. That at once, helicopters are a tremendous asset on the battlefield, but it doesn't take all that much to bring that era of helicopter down.
The helicopter would become obsolete as a reconnaissance and weapons platform if it couldn't survive future battlefields where the need for information would be crucial. In the aftermath of Vietnam, Fort Rucker, Alabama became the home of Army aviation. Some aviation visionaries, members of a group who became known as the Council of Colonels, reconvened in their old Army war room. In the early 1980s, their task was to peer into the future and imagine what type of helicopter would be needed for the 21st century. To accomplish their goal, they would need the support of military and aviation experts in Washington, D.C., as well as some of the best scientific and aviation engineering talent this country had to offer.
They had a vision of taking this helicopter a step farther, a leap farther, and that was what we call the LHX, what is today the Comanche.
The first step was to define the ideal reconnaissance attack helicopter, regardless of how much that pushed the limits of technology.
What we wanted to do was replace a very aging fleet of aircraft that for the most part were older than the youngsters who were operating them.
Reconnaissance in Vietnam was basically based on the eyeball. With the technology that we saw coming along in the early 80s, we believed that we could enhance that tremendously with other type sensors.
It had to be able to operate at night in bad weather. It had to have long-range weapon systems. It had to operate alone behind enemy lines.
Could penetrate sophisticated defenses, could go deep, go fast, survive, be almost around the clock in terms of its ability to operate, and to be lethal and survivable.
Maneuverability, agility, and dash speed are the key to survivability on a battlefield.
Now, we did not know if that was doable or not, but we felt that we had enough technology that it was worth exploring and making that decision at some later time.
But would the notion of a fledgling cybercopter fly in the halls of Congress?
It is extremely difficult to measure the value of reconnaissance on the battlefield because they are non-shooters or non-killers. Therefore, in an analysis point of view, it's hard to demonstrate to the leadership that funds need to be expended for the value of something you can't measure.
By the mid-1980s, it was clear that future battlefields would require not only advanced reconnaissance, but also the ability to strike high-priority targets. Before it was Comanche, it was designated Light Helicopter Experimental, LHX. But could it be built?
A lot of us, sat and thought about a lot of ideas, had a lot of visions. We had some inkling about where the technology was going to go. but certainly not how it was going to get there.
Before the decision that it was a helicopter, of course, it was experimental. It could be anything.
The LHX represented one of the largest challenges ever to the aerospace industry, to design and build a new helicopter using technology that was little more than theory at the time.
We had a lot of, this is impossible. This can't be done. It's never been done. How are you going to do that?
From computer to simulator to test flight, the LHX program would push rotorcraft science and technology a quantum leap into the future. One of the first steps in the LHX process was to test the limits of existing helicopters. During air-to-air combat tests, pilots discovered the maneuvering capabilities a helicopter needed to survive on the battlefield.
The air combat trials gave us a chance to really rack the helicopters around. There was some pretty wild maneuvering that was performed. One of the things we discovered was that we could point the nose of the aircraft, kind of independent of where the aircraft's going. And by pointing quickly, we could get a tactical advantage by getting weapons on target.
They're right on your nose, sir. They're at your 9 o'clock.
The limit of maneuverability of the machine could actually determine the survivability of the machine. It's the first time we ever looked at helicopters as needing maneuvers as part of their basic combat suite.
If you understand the current limits and what limits those helicopters, then you can certainly design for the future. Does it mean that helicopters should be doing loops and rolls all the time? No, but it tests the airframe, it tests the rotors, it tests the engines, it tests the hydraulics, the tail rotors. So it was a way of achieving, the endpoints of technology.
The Army took those lessons learned in air-to-air combat trials to the helicopter industry and asked them to design an aircraft that would dominate the battlefield of the 21st century. There were only two design parameters. The aircraft had to be produced at a relatively low cost, and it had to be lightweight. Otherwise, there were no limits on design or what kind of technologies to use. In fact, some early proposals were not helicopters at all. One imaginative entry was called the X-wing. The X-shaped rotor also served as wings, locking into place once the aircraft had achieved forward flight. Although it was never fully tested, the X-wing appeared not to have the maneuverability required for the LHX and was dropped from consideration. Another contender throughout much of the LHX program was a design called the tilt rotor. After it lifts off vertically, the two large rotors at the end of the wings rotate forward, becoming propellers for fixed-wing flight. This hybrid design offered not only vertical takeoff and landing, but also the speed of a fixed-wing aircraft. Another unique design was the advancing blade concept. The ABC uses two main rotors on a common shaft. Blades rotate in opposite directions, canceling torque and eliminating the need for a tail rotor.
It also eliminated the problem of retreating blade stall, and we mounted some auxiliary propulsion jet engines, was able to take the aircraft into the high 250 knot range. It also had excellent handling qualities. It flew very much like a fixed-wing aircraft because it was so pure.
While all of these rotorcraft flew at least twice as fast as existing helicopters, each had its limitations.
It became very clear very early on that the helicopter was the preferred configuration. The other more advanced configurations were too costly, were too heavy, and actually had some performance disadvantages compared to the helicopter.
Determined to prove a helicopter could do the job, engineers took a standard two-pilot civilian helicopter and created a strange-looking hybrid called the Shadow. It was a flying laboratory for testing many of the components needed to create Comanche.
One of the most interesting tests we flew was the Shadow, which was really a new nose grafted onto an existing helicopter. The Shadow let us put an experimental cockpit in the nose with fly-by-wire flight controls and advanced displays, and let that pilot fly as if it were in his own machine while being tested by the people behind who had regular flight controls to take over if something went wrong.
And what fly-by-wire brought to the Cybermix was an instant response to the pilot's touch.
For agility and maneuverability, a digital flight control system, a fly-by-wire control system, is what's required.
This new digital system would also be much less vulnerable to enemy fire.
Vulnerability of fly-by-wire is very good because you got a lot of wires getting back to those servos, and you continue to fly even though you've taken some pretty massive hits, where a conventional control system only takes one or two and you've lost control.
While fly-by-wire took the LHX into the next dimension of maneuverability, the question remained: could a pilot actually maneuver safely at night in a nap-of-the-earth environment? To test that concept, one early design group created a virtually blind cockpit with nothing but video images and instrumentation to guide the pilot in flight.
If you can picture yourself looking at a TV screen saying, I'm 50 feet from there versus 25 feet. So you were constantly worried, even though you knew you had a safety pilot that could see everything, you were constantly worried about how close am I to that tree, how close am I really to the ground, am I really far enough where my main rotor is not going to hit something, because you literally didn't have any of those cues as a pilot. So you were truly testing and accepting the sensors that were on the aircraft to maintain obstacle avoidance. And I tried real hard, but I just never felt comfortable with that.
The blind cockpit helped early engineers understand the needs of warfighters on a future battlefield. While the Army wanted a rotorcraft that could deal with the complexities of the future, it also wanted it in a single pilot configuration.
The problem that we ran into in the single pilot was, quite frankly, how do you determine cognitive overload? How do you determine enough capability is enough? How do you determine when you go over the threshold and you're starting to endanger the crew?
In a single pilot environment, maybe 70 to 80% of the time you're okay. But where it became a major issue was, how do I manage my time when I've got to navigate, when I've got to do obstacle clearance in the nap-of-the-earth environment, flying close to the ground at night in low light, and by the way, I now have someone shooting at me or I have to go shoot somebody all at the same time.
But a second pilot with an extra set of controls added more than 1,000 pounds of weight to the LHX, exceeding the maximum allowed. For the solution, manufacturers turned to the body of the helicopter. Through ACAP, the all-composite aircraft program, designers found they could create the LHX airframe entirely out of lightweight graphites made from layered polymer and epoxy materials.
Composites were really the keystone of the Comanche helicopter. It's the keystone to building lightweight, survivable aircraft for the future.
With its all-composite airframe, the LHX was also becoming the world's first stealth helicopter.
The low observable capability is extremely important, and that's what provides the survivability for the warfighter as he crosses the line of troops and goes to combat. It defeats the enemy radars and the enemy missiles.
With its composite fuselage and digital controls, the LHX was becoming a completely reinvented helicopter. Engineers created a new bearingless main rotor, substantially increasing maneuverability. 5 blades with advanced swept tips gave the aircraft a low noise signature, much lower than any other helicopter. The fantail was another major innovation. Called a fan-in-fin design, it was slanted to deflect radar detection, and it met 2 additional requirements.
The Army had a requirement that we not use a conventional tail rotor on the helicopter. The tail rotors they found operating in the field in a battle condition, many times they fly literally below the tops of the trees. They found then in those kind of tight quarters that periodically the tail rotor would strike the trees.
Grafted onto an S-76 test ship, the flat, wide blades of the fantail also gave the pilot more thrust to execute aerobatic maneuvers that pushed the helicopter far beyond its earlier capabilities.
The tail rotor control of the aircraft turned out to be a very, very critical part of how we had to fight that close battle. Rather than doing a conventional turn, if you could turn using your directional control pedals and point the aircraft with your pedals, you won the fight 9 out of 10 times in that close battle.
Finally, after many years of designing and testing, the light helicopter experimental with fly-by-wire controls, an all-composite airframe, 2-pilot cockpit, and aerodynamic rotor blades, an all-new helicopter was beginning to take shape. Everything was now in place for the LHX to emerge as the Comanche. April 1991, the LHX contract is announced to the Boeing Sikorsky team.
Thought about, dreamed about, and if you could see all the faces up here, we have won the LHX.
Winning a contract was one thing, but could a 21st century helicopter be built with 20th century technology? Engineers would not only develop new technologies, they would also pioneer new manufacturing methods to achieve the precision required to make Comanche the world's first stealth helicopter.
To meet the radar requirements, we had to have an absolutely clean fuselage, streamlined with no external bumps. Door handles, weapons, landing gear all had to be retractable and flush.
Testing of scale models in a specially designed radar lab showed that composite panels were so precisely aligned, it was impossible for radar to penetrate the seams. But it is more than just seams that defeats enemy radar.
Even a casual glance shows Comanche's body is shaped by more than just aerodynamics. These odd angles are achieved in the composite structure, so the Comanche reflects radar waves away from the antenna that sent them, which reduces the radar signature and adds to the stealth of the aircraft. It's the composite structure that allows us to achieve these angles.
Even the exhaust system incorporated new technology.
We've developed a unique mixing chamber in the tail cone of this aircraft to reduce its heat signature. So the exhaust gases do not exhaust directly into the atmosphere, but they are sent down into the tail cone and mixed with ambient air and then exhausted out the bottom. This cuts down the heat signature, therefore making it less susceptible to infrared missiles.
Survivability on the battlefield was the crucial motive behind all the rigorous testing, and the battlefield came to life in the form of virtual reality simulation.
We built the simulator up front and designed the aircraft based on what we learned from simulation.
Before we build the first production aircraft, using new simulation approaches, we can build 100 different production versions of Comanche before the first one hits the manufacturing floor.
Simulation's a complex game. It's safe to say simulation is nothing like video games. In fact, modern test simulators mimic the behavior of the aircraft by testing every single component as it flies. If you can imagine that we actually calculate all the forces on a rotor blade based on how it's behaving, and then sum those forces up, that's how the simulation gives us the answers.
We wanted the Army pilot in as early as possible to view the design in his battlefield environment.
Engaging. Okay, now fires away. Target engaged and destroyed.
Remass.
New developing technologies in the MEP, the Mission Equipment Package, would expand Comanche's combat capabilities. The need to see everything on the battlefield while flying at night was an early challenge for the MEP.
At that time, the only way we had to operate at night were with night vision goggles, which have a limited field of view. You have the sensation of looking out through a couple of soda straws, and to see anything to the side, of course, you had to move your head around.
That led to the advanced development of a key component in the Mission Equipment Package, a sensor system called FLIR, forward-looking infrared. This is the pilot's eyes on the battlefield. Infrared sensors mounted on the front of the aircraft feed video images of everything: terrain, targets, obstacles, into miniature video displays in the pilot's helmet. The images are projected in real time into a pair of goggles inside the helmet. It gives the pilot clearer vision of the battlefield than he would have with the naked eye.
The forward-looking infrared FLIR system actually generates an image based on thermal data, as opposed to the visible data that your eye sees. It has a detector that senses very small changes in the temperature of the outside scene and uses that to generate a video image.
While forward-looking infrared gave the pilot a good view of the terrain at night, he still had to keep an eye on cockpit images and gauges, while also looking ahead for obstacles in his flight path.
That capability then had to be translated to a helmet-mounted display so that the pilot could fly the aircraft in the same manner that he did during the day, which was with his head up and his eyes out, not flying, looking down into the cockpit at a head-down display.
It was called Heads Up. All flight data, speed, altitude, course, and position, everything a pilot would normally observe on the cockpit instruments, would be projected over real-time terrain pictures sent to the helmet by FLIR sensors. Pilots call it symbology. Furthermore, the helmet would have a magnetic tracking system that links the pilot's eyes to the weapons, targeting, and FLIR systems. Whenever the pilot's head moves, the images move in synchronization.
The imagery stays fixed to the real world and no longer rolls with his head, and it enables him to fly and after the Earth much more safely.
Okay, let me go ahead and get that report out there.
Compensating for head roll in the targeting tracking system was a breakthrough for the mission equipment package.
One of the features of the targeting and tracking system is that wherever the pilot looks is where the weapons are pointed. He can look down at a target.
Roger, I've got targets.
Put the cursor over it.
We'll go ahead and identify.
Lock onto that target and launch the weapons.
Missiles launched. It's ahead. We got ahead.
With Comanche, the gun is slewed to the helmet. We can then point the gun with the helmet, and the elapsed time is literally almost 0 seconds.
And it's like a quick draw. It's like two cowboys standing on the street. The guy who gets his gun out of the holster first and gets the bullet pointed at you and launched at you is probably going to win the fight.
But was the aided targeting system too much of a good thing? The leapfrog in technology created sensory overload for pilots. They now had too much visual information to process.
What we found was with the new forward-looking infrared sensor, they were being saturated with information.
All the onboard sensors and the outputs for the display.
Rapid advances in computing power over the past decade gave mission engineers the answer to pilot overload.
Taking out that directional
New computers that could sort out and prioritize the glut of information saturating the pilot's field of view. Comanche's supercomputer can process 1 billion bits of information per second. It is this computing power that enables everything to function together.
The fiber optic data buses on Comanche move information from the sensors to the computers at the rate of 100 megabytes per second. If your home computer were that fast, you could download 2,500 pictures off the internet in just 1 second.
One of the software packages that we have on board is a target threat management software package.
Jared, you can unmask at will. Roger, unmasking now. And we are exposed, taking a picture. Roger. And we do have targets, remasking. Roger, remasking now.
Once the targets are detected and classified, they're prioritized. And that priority is presented to the aircrew in terms of chipsets. The higher priority chipsets are presented first. An example of a higher priority would be a helicopter moving towards you. That would have a higher priority over, say, a vehicle that's a ground vehicle moving away.
I have targets and remaps.
Advanced infrared sensors, real-world helmet displays, eyeball targeting systems, digital flight controls, all connected by supercomputers, combined with the other innovations of LHX to make a cybernetic whole. Comanche, the cybercopter first envisioned by the Council of Colonels, was now a reality. January 4th, 1996. A mild winter day at the Test Flight Center in South Florida. After more than 15 years of theory, testing, and simulated flight, the first Comanche rolls out of the hangar. The moment of truth had come at last. It was time to fly. While ground crews made their final preparations, workers at the flight center began to line the fences in anticipation.
I would say lifting the Comanche off on the first flight, yeah, we were certain it was going to work. We were totally confident in the aircraft.
327, taxi to runway 27, winds are variable 330 to 360 at 10. Altimeter is 3015. 3015, Roger.
I will admit that just before we lifted off, I asked Bob Gradle, who was in the other seat, take a deep breath and decide, are we really going to do this? And he said yes, and so we just did a very deliberate liftoff from the ground.
And we did a survey up here. Everybody is ready and cleared ride at 34, lift to hover. Roger that. I think we can go ahead and hover. I think you can too. You pretty much got hands-off hover handling qualities here.
It's exciting. It's kind of indescribable for a test pilot.
Going into the forward air taxi at this point. Okay, we'll go 10 knots, take it steady, and then recovery. And he's cleared for 10 knots forward.
There were no accelerated maneuvers on that first flight. None of the rolls and snap turns as practiced in previous test aircraft and countless simulator runs. Just a few low-level, low-stress procedures to test the controls.
The biggest risk that this program faced at first flight was the flight control system. That was by far the largest departure we've made from any other conventional helicopter. It turned out, primarily because of the simulation we've done, to be a non-event.
2, 1.
It was just a shining star. Where there were no problems, there were no glitches, there were no anomalies, and so the thing that should have made us most nervous, we were in fact very comfortable with, primarily because of the simulation that we've done.
And of course our fabulous crew, the people that prepare the aircraft for the flight, and I think would probably have ridden along on the sides of the wings if they could have, were there to congratulate us and express their pride, and you know that the feeling's very mutual, as you can all imagine, and so that's another chance to really enjoy what you've become part of, which is a really great team.
The small team that conducted Comanche's first flight test proudly represented thousands more who contributed to make this day an overwhelming success. There would be more than 100 flights over the next 3 years, each one pushing the test flight envelope just a little further.
It's a very laborious process, and one that takes a team for a typical test aircraft that might be between 25 and 40 people working full-time, literally 24 hours a day, to keep the system going.
As a test pilot, my job is to fly the aircraft very precisely. It would be like asking you to drive your car exactly along the center line of the road without varying more than a couple feet, and exactly at 65 miles an hour. And 64 wouldn't be good, and 66 wouldn't be good. It has to be 65, and you have to do that for an hour.
The flight tests are designed to see how well the construction of the composite airframe, digital controls, fan tail, and every other innovation on the Comanche perform. But it's not just the pilots who are responsible for its success. Every test flight is like a scientific expedition requiring hours of preparation. Before each flight, engineers and maintenance personnel go over every inch of the aircraft, checking panels, making sure all components are in place and properly secured, and testing all the digital equipment and sensors that will be used to measure the Comanche's performance.
A typical day at the Test Flight Center is interesting. We'll come in at 6 a.m., for example, and get a briefing where the team sits around and discusses exactly what we'll do during the test flight.
Pilots will be Nick Lapis and John Armbrust. We're also taking Joe Summers.
In the briefing, pilots, engineers, and other members of the test flight team review the flight card, the list of maneuvers Comanche will perform on that day.
Every single maneuver is scripted. We might carry a 25-page card that literally lists every action that will take place, every switch that flipped.
While we're briefing, our mechanics are doing final checks on the aircraft. The aircraft is powered up, so the instrumentation system that's installed on the aircraft to gather data is all warmed up, constant temperatures, etc.
Over 3,000 sensors installed on the aircraft, identified by orange-colored wiring, remotely feed data to engineers who monitor Comanche's performance through a process called telemetry.
Telemetry is an integral part of the flight test program. It's where we monitor the aircraft's health, just very much like a doctor monitors the health of a patient.
Okay, that concludes our pre-flight briefing. Have a good flight, gentlemen.
From then, the pilots break off, and the two pilots who are assigned to fly in the test aircraft then get together and go over any cockpit-related details. Okay, if I do this, then I want you to do that. And if I'm looking there, then please do this, or tell me when you see this. Those sort of details that aren't really appropriate for a larger briefing.
A final walk-around and pre-flight inspection by the pilots, and they are ready to fly.
While we're flying the maneuvers that are on that card, there are engineers in telemetry who are looking at exactly what's happening in the aircraft. Telemetry could have as many as 10 or 12 engineers, each one looking at a particular section. One guy might be looking at nothing but the hydraulic systems and how they're behaving, making sure the valves are open and closing properly, that the temperatures are right and the pressures aren't being exceeded. Another might be looking at the stresses on the rotor blades to make sure the rotors can withstand the stresses we experience in flight. As we maneuver the aircraft, we use what's called a build-up technique, going to higher and higher speeds and higher loads. So we'll maneuver gently at first, and the engineers will say, yes, you're okay to go on. So we maneuver more severely and keep on going more and more until we reach some limits.
With its extreme agility and sophisticated flight controls, Comanche is optimized to perform its missions on the battlefield.
Here we go. That's pretty, yep.
With its digital fly-by-wire control system, the Comanche is the most agile helicopter in the world. The pilot controls its agility through the sidearm controller. With it, he can make inputs to pitch, roll, and yaw. Essentially, we can point the Comanche wherever we want it to go.
Even at this stage of testing, it's clear that Comanche flies like no other helicopter.
One of the things I was struck with when I first flew the Comanche was at once how responsive the aircraft was, but also how controllable it was. The Comanche's flight controls allow a roll rate of 100 degrees per second in about 1/3 the time of a conventional helicopter. The Comanche's fantail has enough thrust so the Comanche can fly 80 knots left or right sideward flight and 80 knots backward. That's twice what today's fleet can fly. Comanche has a cruise speed of 176 knots with a full war load. Its velocity not to exceed, the VNE, is over 200 knots in a dive. The Comanche is the only aircraft that can do a snap turn, and that is the ability to point the nose independent of the direction of travel, so we can bring weapons to bear at speeds up to 110 knots. And that means in an air combat battle with another helicopter, the Comanche pilot gets the ticket home.
Power, agility, maneuverability, they all, of course, relate directly to how aggressively you can prosecute a battle or fight the aircraft.
I see my job as being sure that I put this aircraft through its paces, and I want to see the problems first. I never want to have an operational pilot find the problem that I didn't see first. I really have no work at all compared to what the Army pilot does once he puts this aircraft in the nap of the earth, low altitude environment at night, trying to dodge threats, find his targets, call the proper fire support in. And so that's what we want to be sure is we hand them a platform that's a good, reliable tool for them to use.
Although it isn't scheduled to be battle-ready until about 2006, the Army is already training pilots to fly Comanche, testing their skills in virtual reality combat missions set in the early part of the new century. If and when Comanche is called to battle, it will be the most versatile weapon the Army has ever fielded. It will play a role in a multitude of hostile scenarios, including some we have already witnessed, that serve as a warning of things to come. Attacks on American embassies, terrorists striking at will with everything from car bombs to chemical and biological weapons. Acts of aggression not confined to a formal battlefield, where there is no clear enemy to confront. And with weapons of mass destruction proliferating throughout the world, we are left with the question, how do we defend or retaliate against the threat of random attack? This peaceful setting in Pennsylvania is the training ground for the military's defense against acts of war. At the Center for Strategic Leadership on the campus of the Army War College, defense strategies for the new century, reflecting a more complex geopolitical world, are first created. In this high-security environment, top military and civilian leaders play out futuristic war scenarios in the abstract. Scenarios which are field-tested using advanced technology in settings that combine actual and virtual reality. Here at Fort Hood, Texas, in an advanced warfighting experiment, the Army assesses the theories and weapons of the digital battlefield. The Army conducts these war games independently or combined with joint services, using information dominance to win hypothetical battles. Comanche engages in the exercises through the Comanche portable cockpit. Inside this mobile simulator, pilots not only fly the Cybercopter, they also get experience making combat decisions.
Targets are howitzers, one air defense piece, and armor.
Decisions that are made by the people who are actually out at the front on the battlefield are decisions that in the past have been made further in the rear by senior commanders. And now we have pilots that will be making those kind of decisions.
I have targets and a strobe at 12 o'clock, reman.
The simulation permits you to push a weapon system to its maximum capability and even to the point of being destroyed, getting killed. If you don't push to that point in simulation, you never find the farthest that you can push that weapon system, how much it's capable of doing for the battlefield commander.
Air defense as the primary target.
Nowhere is Comanche pushed further than in the full motion-based simulator in Connecticut, where pilots fly entire missions designed to test the limits of both man and machine. In this virtual reality world, the time is somewhere after the year 2006.
The next waypoint, observation post on the map.
Comanche is called to action. With a range of more than 1,200 nautical miles, it self-deploys to a waiting aircraft carrier where it will be armed and refueled. Under cover of darkness, it departs on its mission. It is headed to a region where a belligerent neighbor has invaded a U.S. ally. A digital map and GPS are the heart of the navigation system, providing critical waypoints to the area of engagement. Flying nap of the Earth, the pilots use FLIR for terrain and obstacle avoidance. Its reduced noise signature enables Comanche to fly over areas where other helicopters would be easily detected. Sensors feeding images into pilots' helmets turn night into day. Meanwhile, the command and control center follows Comanche's progress using a real-time data link. By daybreak, Comanche is deep in enemy territory. Comanche's positive pressurized cockpit protects the crew from nuclear, biological, or chemical contamination. Its infrared signature is only 1/4 that of any combat helicopter, reducing the threat from heat-seeking missiles. On radar screens, it appears almost 300 times smaller, making it virtually invisible. The pilots approach a ridgeline, their designated observation point.
Vegetation on top looks like that might be a good place to set up an OP.
Roger.
Okay, that's good.
Dropping in behind a line of trees, they mask their location from the enemy. They briefly unmask,
We are exposed. Roger. You're taking a picture.
allowing Comanche's FLIR and sensors to scan the area for enemy targets.
Targets.
We have targets.
Roger, remasking now.
The ATDC, Aided Target Detection and Classification System, not only identifies and prioritizes enemy targets, it also identifies friendly forces.
Yes, we have 4 enemy targets and 1 friendly.
Instantly, Comanche's data links send the encrypted battlefield information out to a broad array of air, land, and sea resources. J-stars, AWACS, satellites, armor, artillery. Even the individual soldier in the field receives vital information. Within seconds, command and control takes action based on the reconnaissance.
They're leaving themselves vulnerable. We can split them, have Second Corps come down. We've got them isolated down here in the south, and we can envelop these guys, cut them off, and stop the 4th from ever coming up.
Orders are to take out the air defense artillery. Okay.
Rising above the trees once again, Comanche's hover and altitude hold keep the aircraft in a constrained position as it readies to fire. Its automated targeting system assigns the appropriate weapon, selected from its array of missiles and rockets.
Missiles out.
In a tactical move, Comanche's crew takes out the Air Defense Artillery Unit, the ADA.
10 seconds. And lasing.
Target, got a splash.
We got him. Better send back a BDM. I will.
With the primary threat to other aircraft destroyed, Comanche pilots send out a battle damage assessment, a BDA, to the network.
Yep, I'll let Brigade know what just happened, so that way the guys...
Mission completed. Comanche returns to its virtual reality base. By the time Comanche goes into service early in the new century, its role could be expanded beyond what it is in virtual reality today. One role that is now being actively studied in a battle lab simulation would have the Comanche extend its reach over the battlefield through the use of small, remote-controlled, unmanned air vehicles, UAVs.
Roger, I have an armored column.
In this scenario, a UAV with cameras and other sensing devices flies high above the ground, giving Comanche pilots flying at treetop level a completely different perspective.
So before we cross, say, the next ridge line that we can't physically see, we use the UAV sensors package, his infrared feed from 5,000 or 6,000 feet to give us that bird's eye view of immediate intelligence before we cross that next ridge or maybe several kilometers in front of us.
See if I can correlate that.
The UAV would initially be guided by a ground control station using satellite maps for direction.
What we think the 24th is crossing the river there, okay?
But control of the UAV can be handed off to a Comanche hidden in a strategic position deep inside the battlefield. It would use the UAV to snoop even deeper into sensitive areas of the battlefield without risking the Comanche or its team.
I can actually assume control of the UAV and have the UAV fly that line that I draw on my map. And it's almost as simple as an etch-a-sketch line. I draw it, put the points where I want it to go, send the flight plan digitally back to the UAV, and it flies where I tell it to go.
Fly right up the ridge line.
With its multitude of mission capabilities, Comanche is clearly destined to be the quarterback of the information battlefield. But what about its first official mission, when a military convoy escorted it to the nation's capital? On that assignment, this astonishing aircraft was unveiled to a crowd of dignitaries, military leaders, and members of the public as a symbol of the Army's strategy of information dominance for the future. It had been nearly 20 years since the Council of Colonels first met to rethink the helicopter.
I think Comanches will be flying in 2050. In my opinion, it's the last pure helicopter the Army will ever develop. We may be into anti-gravity machines after Comanche.
What really matters is that second or first lieutenant, or that W1 or W2 warrant officer pilot that's in the field with it when it's snowing and 4 o'clock and dark, and he has to take off because somebody is doing something they shouldn't and threatening some of our people, that he can get the job done and that he thinks that we did a good job. That's the bottom line.
With the continued support for Comanche, I'm confident that we in Army Aviation can get this system to the field, and we can make it a reality, and it will be the best system out there for our American soldiers.
Comanche is the latest of a new generation of weapons designed to minimize casualties on both sides and bring a speedy resolution to any future armed conflicts. Weapons so intelligent and difficult to detect, they border on the indefensible. They may even make peace, not war, the only viable option.